And we're back. So this is day 2, section 5.4, indefinite integrals and the net change theorem. All right. So just to kind of recap what we talked about yesterday. What we're doing now is taking integrals and taking them from a concrete area to an indefinite integral. From a definite integral to an indefinite integral. From a concrete area, from, if I know my endpoints of A to B along the curve, I can figure out what my area is along that curve by taking the integral and doing top minus bottom, by taking the antiderivative and taking top minus bottom, plugging in to the antiderivative. But now what we're going to change it to, now what we're going to shift to is now if I don't know the endpoints, I can just use the antiderivative as a function. Rather than just a number, I can use the antiderivative as a function, just including my constant, right? So the antiderivative of x squared would be x to the third over 3. Remember, take up the power, divide by the power, and then plus our constant in the end, okay? Please, again, make sure you distinguish between the difference between, make sure you distinguish the difference between definite integral and indefinite integral. Definite integral is an area. Your output is a number. The indefinite integral, the output is a function, an equation, okay? And then we talked about this table. Again, if you need to, this is still up online on the notes, so make sure that you print that out if you'd like it. Have that handy for you guys. And then we just kind of worked with the equations here, right? We're just creating using the antiderivatives to create the indefinite integral. And then we did some definite integral stuff as well. So let's evaluate this. Take a look here. Is this definite or indefinite? Definite. All right. So I'm going to evaluate from 1 to 9, 2t squared plus t squared, square root of t minus 1, all over t squared. At the beginning of this, it looks like really difficult, really weird, really involved equations. But to find the integral, the best thing to do right at the beginning is to reduce it down. See if we can do anything to it to turn it into some sort of polynomial. Because as of right now, do we know how to calculate the integral of a quotient? Not yet, right? We haven't gotten there yet. And I don't think we will get there. That's like a top 2 thing. So we don't really know how to calculate the integral of quotient. So maybe I can do something to it to turn it into something that I can evaluate. So I got from 1 to 9. Here's what I can do. I can separate that's a 2. I can separate each part of the numerator with each part of the denominator, or with that t squared in the denominator. Now, how does that help us? Well, that helps us because I can eliminate this. So from 1 to 9, 2 plus, eliminate this, square root of t, minus, and let's just make that t to the negative second power, dt. And now I take the antiderivative. I take the antiderivative and find the general antiderivative to be 2t plus. Now, isn't this, I should have made this t to the 1/2, right? We're learning that for the first time today in Honors Algebra 2. We're talking about rational exponents, turning radicals into fractional exponents, blowing their mind a little bit. And then so we got t to the 1/2 power. So kick it up. T to the 1.5 power over 1.5. Again, you're going to see the book use fractions there. You're going to see the book use t to the 3/2 power over 3/2, which is pretty like 2/3 times that thing. So if you ever look in the book and see a different answer with a fractional exponent like that, that's okay. That's to be expected. And then we've got t to the -1 power over -1. take up the power, which means raise the value of it. So 100 is the integral. All right, so just to evaluate, and then this is from 1 to 9. So just simplifying that a little bit, we got 2t plus t to the 1.5 over 1.5, and the only thing I can do there is just plus t to the negative 1 from 1 to 9. And at that point, we plug in. We do top minus bottom. We say 2 times 9 plus 9 to the 1.5 over 1.5 plus 9 to the negative 1. All of that minus all of this. 2 times 1 plus 1 to the 1.5 over 1.5 plus 1 to the negative 1. So let's evaluate each piece here. This is going to be 18 plus 9 to the 1.5 divided by 1.5. I didn't need to put that in parentheses, that's okay though. Plus 9 to the negative 1. So that's going to get me 36.1 repeating, or 36 and 1/9. We good?
Why don't you have the 1 on the 9, like, over 1? Or that would
Say what?
because then you take the power to the
Be more specific. Where are you looking?
the not plus 9 to the negative first power.
Yeah?
Why isn't it over 1?
It doesn't, because you don't need it. Because it was over 1 here, right?
Oh, plus, that's why I got that.
You good?
Yeah.
Okay, I have no idea. I couldn't follow what you were saying. Yeah.
So what kind of confuses me is the indefinite integral.
Yes.
For the integral, it's the area, right? Like that's what the integral is.
A definite integral, yes.
So indefinite, so that value, like with just that function alone, the value that you would get isn't even anything, right? You get what I'm saying?
No.
Because for the definite integral, right?
Yeah.
You're getting that. So like.
Well, I've got to subtract this thing.
Yeah.
Right.
But then the indefinite, that value is.
What you get for an indefinite integral, the output is a function.
Yeah.
The output is an equation.
But that equation doesn't even get you the integral.
That equation is the indefinite integral that you could use to find the area.
Yeah, okay.
Does that make sense?
Yeah.
It's an equation that the output of that equation will give you area once you plug things in. Does that make sense?
Yeah, no, I get it. I just didn't know if because with just that function alone, if you use that function without having two values,
Right.
you wouldn't get anything.
Right. It's just like a setup to get you ready to find the area. Does that make sense?
Yeah.
Yeah. And then let's take the second part here, 2 times 1. So 2 plus 1 to the 1.5 is just 1. So 1 over 1.5 plus 1 to the negative 1 is just 1. So 3.6 repeating. I got that. So we have 32. No, I'm not going to do that anymore. 36.1 plus, oh no, minus 2. Minus 3.6. So 32.4 repeating. Oops, 32.4 repeating. And there's my answer. So you said 32.4. Questions about that? Again, that honestly, that could have been on the quiz, right? Like that would be really hard. Probably on the quiz, but that still could be on the quiz. We're still just taking a definite interval there, right? Going from 1 to 9, just using that top minus bottom rule. This is kind of an involved question. All right, so the last thing that we'll cover in this section is called the net change theorem. The net change theorem, and it's really just application of antiderivatives of integrals. Okay. The integral of a rate of change is basically the net change of any, if you apply it to anything, it's the net change from one piece to the next, right? So if I take the integral from a to b, definite integral from a to b, of f prime of dx. It's just f of b minus f of a. That's just top minus bottom, right? Plugging in f, finding the antiderivative, plugging in f, and plugging in a and plugging in b to find the difference between the two. This principle can be applied to all rates of change in natural and social sciences that we talked about in section 3.7, kind of didn't. Here are a few instances, and this is just, I'm giving you kind of ideas on where this can be applied. Okay, you don't necessarily have to write all this stuff down. I'm just showing you this is where this stuff can be applied. This isn't new material. This is just application of what we've been learning. If V of t is the volume of water in a reservoir at time t, then its derivative is the rate at which the water flows into that reservoir. Okay, because the rate of change is the derivative, right? So therefore, if I take the integral from any two time periods, time 1 to time 2, and I plug it into the original function, and that is the change in the amount of water in the reservoir between the two time periods. So if you can calculate the rate of change, if you've got a function of the rate of change, you can find the integral. The integral, when you plug it in top to bottom, top minus bottom, between those two time periods, that's the net change in between those two time periods. The net change in between those two time periods. Okay, if C of t is the concentration of a product of a chemical reaction at time t, then the rate of reaction is the derivative. So that's an application, it's a chemistry application of the derivative. So if I take the two time periods and I plug in into that derivative, if I plug that into that function, those two time periods, that's the net change in the concentration of those two time periods. So you can use the integral within these different topics. You can use the idea of an integral to find the net change in those things. Let me give you a couple more examples. If the mass of a rod measured from left to right, from the left end to a point x is m of x is the linear density, rho, I think that's a Greek letter, rho of x, is m prime of x. So therefore, if I find the integral in between those two, plug my endpoints into my original function, that's the mass of the segment of the rod that lies between those two values. Okay? The rate of growth of population can be modeled by an integral. Okay? If I know if the rate of growth of a population is some function dn dt, then if I can take that from any two time periods and plug it into that formula, plug it into that derivative there, then I know that that's the net change in population during the time period. So what am I really doing with all of these? I'm taking two values and finding at two different times, I'm observing two different things. Usually time, the density one was two different spaces. But I'm taking two different times and finding endpoints in these two different times, and then I'm plugging those into, if I know functions and their derivatives and I can have applications of them, then I can plug those in, and that would be the net change in between those two time periods. And as you can see, I mean, I'm not going to go through all of them, but there's a lot of different applications. One application that we have been studying all along is, displacement, velocity, and acceleration, right? We know that if I've got the displacement, I can find the derivative of that to find the velocity, and I can find the derivative of velocity to find acceleration. If an object moves along a straight line with position function s of t, then its velocity is v of t. So if I want to find, I can take the integral from time period 1 to time period 2 of v of t dt. I can take the position and plug it in left to right. That's going to be equal to the integral from time 1 to time 2 of v of t dt. It's the net change of position or displacement of the particle during that time period from 1 to 2. Because that makes sense. If I plug it in here, time 2 to time 1, and find the difference between the two, that's the change in position from time 1 to time 2 to time 1, whatever, between those two time periods. And that will give me the full displacement between those two time periods. And let's take a look at this example. This is our last example. We're not going to, those of you print out the notes, I'm not going to do the last example. A particle moves along a line, so then its velocity at time t is v of t is equal to t squared minus t minus 6, measured in meters per second. Find the displacement of the particle between times 1 to 4. Find the displacement of the particle between times 1 to 4. What is this truly asking me to do? This is actually asking me to find the integral. If I want the displacement, all I need to do is find the integral. The integral where? From 1 to 4. The integral from 1 to 4 of b of t dt. Right? That's what part A is really asking me to do. Find the integral from 1 to 4 of b of t dt. Which means, once I plug b of t dt in, I just plug b of t in, that's going to be t squared minus t minus 6 dt. Okay, to evaluate this is just another definite integral that we can evaluate. I find the antiderivative. That's t to the third over 3 minus t squared over 2 minus 6t from 1 to 4. Which makes sense because think about what we just did there. Think about what we just evaluated. We took that v of t, which is our velocity function. We found the antiderivative of it. So if I'm working backwards, I have the velocity. I work backwards. What am I finding? Position, right? I'm finding position. And all I'm going to do is run those two values, 4 to the third over 3 minus 4 squared over 2 minus 6 times 4 minus 1 to the third over 3 minus 1 squared over 2 minus 6 times 1. And all I'm doing there is plugging in my two time values into the position function to see displacement. To see displacement, to find the full displacement of this thing. So let's plug it in. Let's see what we got. 4 to the third over 3 minus, okay, that's 16 over 2, so 8. Oh, I shouldn't have hit it, but that's okay. Minus 6 times 4 is 24. So negative 10.6, which means, this went in a negative direction for that, right? And I'm in the negative direction at positive 4 time. Minus, I don't know, I wrote such a big print. Minus, and we got 1 over 3, 1/3, minus 1 over 2, 0.5, minus 6. So negative 6.16. Oops, that's an eraser. Negative 6.16 repeat. So this gives me a negative 10.6. Plus 6.16. So negative 4.5. I'm gonna double check my answer. Yep, negative 4.5. Displacement, right? That's displacement. That is saying I've moved in the opposite direction 4.5 meters. I've moved in the opposite direction 4.5 meters, whatever negative direction that is. Now, that is not distance traveled. I end up, say if right was in the positive direction, left was in the negative direction, I've ended up at negative 4.5. That's my net change, right? That's my net change. So, but what if I wanted, do I know what happened in between there? How far, maybe it moved right, then it moved left, maybe it moved far left, and then it came back a little bit. I don't know what happened in between. All I know is that the net change is negative 4.5. The net position is negative 4.5. So what if I wanted to figure out, well, how much did it actually travel during that time period? Well, I have to take into account how much it's moving in the negative direction and how much it's moving in the positive direction. So I have to figure out where it's moving negative and where it's moving positive. Now to do so, that's all part A. To do so, I'm going to need to figure out when it's changing from negative to positive, which means I need to find the zeros of this thing. negative t squared minus t minus 6. That's the original function that we were given up top. Okay? Because I want to know when it's a negative velocity to when it's a positive velocity, right? I want to know when the velocity is going negative and when the velocity is going positive, when it's moving backward to when it's moving forward. Because what I want to do is if it's moving backward, I want to take the opposite of that, right? If it's moving backward, if I want to find the distance traveled, I want to take whenever it's moving in the negative direction and turn that back positive. And then I'm going to take the positive direction, moving into positive velocity, and leave it positive. Because that's going to give me my full distance traveled. So where is it going to actually be a negative velocity? Well, let's take a look at the zeros of this thing. That's t minus 3 and t plus 2. So t is equal to 3, t is equal to negative 2. So what's the only zero that I care about? I care about the 3.
3, yeah. I was looking at it.
I care about the 3. Why is that the only one that I care about? Well, time value being negative, I don't really consider that. But more importantly, even if this had both come out positive, it's within the range. It's within my range of my integral. I'm only looking at from time period 1 to 4. 3 is within time 1 to 4. So this is the only one that I. Three, this one is the only one that I care about. I don't even worry about the negative 2. Okay? So now I have to run a little line test to see, okay, where is it negative and where is it positive? Is it negative below 3? Or is it negative above 3? I don't know, because I got to figure out where to make it negative and where to take the opposite. So if I plug in something below 3, let's see what happens. Let's plug in 0. Well, I would get negative 6, won't I? If I plug in 0, I get a negative number. If I plug in 4, 4 squared minus 4 is 12, minus 6 is positive 6. I will get a positive number. So everything to the right of 3 is a positive velocity, and everything to the left of 3 is a negative velocity. Well, until negative 2, right? But we don't worry about that over there. What do I worry about? I worry about going from 1 to 4, right? So here's what I need to do. I need to turn my negative velocities positive, because that's going to give me my net distance, right? My total distance traveled. So I'm going to take my integral from 1 to 3 and turn it positive. Right? Because that's going to be a net. If I just take the integral from 1 to 3 dt, that's going to be a negative displacement, right? I'm moving in the negative direction from 1 to 3. So if I want total distance traveled, I want the opposite of that distance. I want to turn that positive. And then I'm going to add it 3 to 4. Because that's going to be my positive velocity. Does that make sense? I know that was really kind of convoluted there, but what I did there was figure out at what times it was moving in the negative direction and what times it was moving in the positive direction. And then I take the time it's moving in the negative direction and find the opposite of that integral, because that's going to give me how much it moved as a positive value, as like the absolute value. That's going to take it how much it moved in the negative direction and just take that chunk as a positive. Yeah.
From the negative or the 1 to 3 or whatever, was
Yeah.
that in the position versus time graph? Would that be in the bottom?
Yeah, because that's well, in the position versus time graph, that's decreasing.
Okay, but it won't be 0. It won't be negative.
It might not be negative, right? Because if I'm thinking about the position,
Because you don't know where you start. At.
right, and if I'm thinking about the position, here to here, then that must mean that from here to here is a negative velocity, right? Which makes sense because from there to there, the derivative of that is the velocity. that must be in the negatives, which that's what we did here. To figure out, that's like old chapter 3 or chapter 4, doing that test where it's negative to positive test. You know what I mean? So again, what we did there was found where the velocity changed from negative to positive, and then everywhere it's negative, I want to take the positive value of it. I want to take like the absolute value of it. So let's go ahead and do that. Negative, switching colors, okay. T squared minus t minus 6, t squared minus t minus 6, dt, plus, from 3 to 4, t squared minus t minus 6, dt. Okay, let's find both integrals. Down a little bit more. So we've got t to the third, and this is a negative here. T to the third minus, over 3, minus t squared minus 6t from 1 to 3.
T squared over 2, right?
Ah! Yep, thanks. Sometimes I forget those. That's not good. Plus t to the third over 3 minus t squared over 2 minus 16. These are minuses, right? Yep. From 3 to 4. So now we evaluate this to be 3 to the third over 3 minus 3 squared over 2 minus 6 times 3 minus 1 to the third over 3 minus 1 squared over 2 minus 6 plus 4 to the third, 4 to the third over 3 minus 4 squared over 2 minus 6 times 4 minus 3 to the third over 3. I don't need another parenthesis in there. 3 to the third over 3 minus 3 squared over 2 minus 6 times 3. Now, when I run this value, when I find this value, that's 27 over 3, which is 9. So 9 minus 9 over 2, so 4.5, minus 18. And then all of that minus 1/3, minus 1/2, minus 6. That's a negative value, and it's going to turn it back positive. See what I did there? That's the only time where that integral is going to come out negative, so it's going to turn it back positive. Now this should all be positive. So I take 4 to the third. Oops, no. 4 to the third over 3. So 21.3 minus, okay, so that's 16 over 2, which is 8, minus 24. So negative 10.6 minus.
Why didn't you, I might be dumb, why didn't you subtract the 7.3 from the 13.5?
You subtracted the other value to get 7.3.
Okay.
Yeah, I did that, negative 13.5 minus
I didn't
this.
see the answer. Okay.
Does that make sense?
Got it.
Okay. And then we're at negative 10.6. Let me make sure that came out right. I'm going to run that number again. 4 to the third, 4 to the third over 3. Over 3. I'm just doing that one more time. Minus 16 over 2, which is 8. Minus 24. Negative 10.6. Okay. Hold on. Hold please. Hello, Mr. Castanizer. Yeah. Yep. 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 See ya. Okay. And then we got 3 to the third. 3 3 to the third, minus, over 3. No, over 3. Minus 3 squared over 2, minus 4.5. Oh, isn't that third? Yeah, it's that same thing as well. I already lost it in my calculator up there though. Was it 13.5? Negative 13.5. So it was negative 10.6. And then negative 13.5 minus a negative 13.5, which gets us 2.83. So all of that is 2.83. Positive 2.83. So my total is a 7.3 plus a 2.83. So total distance traveled, I got 10.17 when I did it earlier, but 10.13. I might have rounded a little bit different. 10.13 meters. Questions about that one? That was a good one. I like that problem. That was a good one. All right.